A core device associated with PV systems is the converter, which is based on power electronics. Hence, the topics treated in this chapter are two: DC to DC converter and the DC to AC inverter. Both of them belong to the balance of the system. Let's start with the DC-DC converter by giving you the first definition of the DC-DC converter and then showing the power electronics to be used. Then we shall describe the topologies to step up or down the voltage coming from the PV side, respectively, the buck or the boost converter. Lastly, we will deal with the buck-boost converter, which encompasses the two previous cases, and we will compute its efficiency. In this video, we shall explain the importance of a converter, give you its definition, and then its requirements. Let's start with some basic concepts. A PV module is a voltage-driven current source, and its IV characteristics depends on environment condition, such as the irradiance falling on the module. For each of these curves, we can identify the maximum power point. However, if the load is a simple resistor, as the one depicted in figure with the straight line, then we can see that under different irradiance conditions, the operating point may or may not overlap with the best output of the module. In this case, the solar module can only contribute a portion of the actually available power. In other words, depending on which resistance or load is attached to the PV panel, we have different operating points. Therefore, it is very important that the PV panel is always at the maximum power point of the module and, at the same time, that also delivers a maximum power to the load. The purpose of the DC-DC converter is to decouple the PV voltage from the load voltage so that the PV panel can work at its optimum while the load, such as an LED, a laptop or a car, is supplied with its rated voltage. We have already seen that the maximum power point tracker controls the operating point of the modules, but cannot set it. This task is then performed by the DC-DC converter, which varies the PV voltage in order to draw always the maximum power available. Adding the maximum power point tracker is nothing else than adding an additional circuit that can be also embedded on the board of the converter. The tracker measures the current and voltage at the output side, and according to its algorithm, it sends some signal to the DC-DC converter, for example, to step up or down the voltages between input and output in order to meet the voltage requirements of both PV and the load sides. Of course, the topology can be made more complex depending on the maximum power point tracking algorithm and some other information that might be provided to the MPPT, for example, the temperature of the PV module and the outcome before the load. In this way, the PV power is maximized by measuring the current and voltage and simultaneously varying the DC-DC voltages. More in general, when we just look at the ideal DC-DC converter, it is a dual port component with a switch in the middle, called the impedance transformer. In other words, to deliver the maximum power from the source to the load, the impedance seen by the DC-DC converter at the left part of the circuit is the same as the one seen by the load at the right part of the circuit. Now, a little bit of definitions before we move forward with the different components as well as different topologies. Here, the concept of duty cycle is described, as it will come back several times. Imagine that you have a time-dependent signal, for example, a voltage, that is periodic with a period Ts. It is possible to further split this period in two time spans. The first is called the T-on, and is when the signal is above 0 volts. That is when the circuit is closed. The second is called the T-off, and is when the voltage is 0. That is when the circuit is disconnected. Then the duty cycle is defined as the ratio between a T-on and the time interval of the one entire cycle. This is the principle of operation of an ideal step-down converter. We shall come back to it soon. Here, we report other ways to write the T-on and the T-off as function of the duty cycle, which is the previously mentioned input signal given by the MPPT tracker. To conclude this video, The DC-DC converter has been defined as an electronic circuit that converts a source of direct current from one voltage level to another, and the objective of an ideal converter is to draw the maximum power from the panel to supply it to the load. There exist three different types of converters: buck converter that decreases the voltage of the PV side, boost converter that increases the voltage, and the buck boost, which includes both previous cases. In the next videos, we shall explain more in detail these three types of converters and their components.